Section 6.4 is about adding, subtracting, and multiplying expressions that have radicals in them. And really the adding and subtracting go together. So the big thing is that you can combine terms that have like radicals, which basically just means that they have the same radical in them when you simplify the radical all the way down. And the way that you combine them is very much like the way that you combine like terms. So like it says right here, where like radicals are similar to like terms, yeah. If you think about what you would do if you were going to add two polynomials together, where then if both polynomials have an x squared term, you could combine those. If they both have an x term, you can combine those. It's the exact same idea. So I stuck in an example like that had some like terms, a couple of different variables, I guess, but if you look at what's there, you got a 3xy squared and an 8xy squared. You could add them, and you get an 11xy squared, right? So like that one and that one are going to have like terms, so you can add them together. The other ones you can't, right? There's an x cubed term, and there's a y term, and there's nothing to combine those with. But the two xy squareds, those are like terms. Same thing with the radicals. So if you look at the example with the like radicals, those first two terms have a square root of 2x in them. So you could combine those and you get the 7 radical 2x on the right side. The other ones you can't do anything. There's a square root of 3x. Well, that's not the same root, right? Because in order for the root to be the same, you need to have the same radicand, which is the thing under the radical, and it has to be the same type of root. So like square root, cube root, fourth root, that kind of thing. So the square root of 3x we can't do anything with because that's a different root than the square root of 2x, right? It's also a different root than the cube root of 3x. So you can't combine the cube root of 3x term and the square root of 3x term because those are different roots, even though the thing underneath the radical is the same. So like radicals, same radicand, same type of root. All right, so not that I think there will be any trick questions in this section or anything, but that is what you would need to get this to work. All right, so number one, if you look at that one, we've got a square root of 5x in both terms. So that doesn't simplify any further, right? There's nothing that you could, like, there's no perfect square that divides 5. Well, other than 1, but that doesn't help, right? So those roots don't simplify any further, and we would have 3 plus 7 times the square root of 5x if we combine like terms. So this is going to be 10 times the square root of 5x. All right, and we can do kind of a similar thing over here in number 2. The cube root of 11 shows up in all 3 terms. So it's 3 terms instead of 2 terms that you can combine together, but you could do it all in one shot if you wanted, where then you could say, well, then this would be 5 minus 8 plus 1 times the cube root of 11. And 5 minus 8 plus 1, that's negative 3 plus 1, so that's negative 2. So negative 2 times the cube root of 11. All right. Oh, and one thing I should mention, this is, I guess, is particularly relevant to number 2 because it's one that has a root that's not a square root. When there's a root that's not a square root and I'm writing it out by hand, I always write in the multiplication dot just to separate the root off more, just so that way it's clear that that 3 is for the cube root, that it's not like cubing a 2, which it might be what it would look like if they were like right on top of each other. And I think in the homework that my lab probably wants you to do it without the multiplication dot, but that's one thing where if I don't write it that way, it looks really weird to me. So like writing it out by hand, I feel compelled to add in the multiplication dot whenever it's a root that's not a square root, right? Because when there's a square root, you don't write in the 2 for square root. So then it's pretty clear what everything's supposed to mean. But when there are cube roots and fourth roots, it's easier for me to read it that way, I guess. So that way, when I write it that way, it looks right. I guess that's really what's going on. But anyway, I kind of always write those that way when it's some root that's not a square root. All right, 3 and 4, we're going to do the same kind of thing, except we got to simplify the roots first this time. So before the roots were ready to go, right? Square root of 5x, cube root of 11, right? There's nothing you can do to those to break them down any further. But with something like number 3, there are things that you can do to break those down a little bit, because 20 is divisible by a perfect square, 4, and 45 is divisible by 9. All right, so let's break these down as far as we can. So we can write that radical 20 as radical 4 times radical 5. And then we're going to write the radical 45 as radical 9 times radical 5. But then square root of 4 is 2, square root of 9 is 3. So we can say, well, this is 3 times 2 radical 5 plus 8 times 3 radical 5. And then 3 times 2 is 6. So 6 radical 5 for that first term. And then the second term, 8 times 3 is 24. So 24 radical 5. And then same roots, right? They're square roots, and more specifically, square root of 5. So we can add the 6 and the 24 and say that that's 30 radical 5. And that's the answer. All right. Number 4. We're kind of playing the same game with number 4, except that now there are x's underneath the radicals. But we're still kind of doing the same thing. So like with the square root of 12x, you can say, all right, well, we can't do anything with the x, but the 12 is divisible by 4. So we can say this is 6x times square root of 4 times the square root of 3x. And then with the 3x cubed, well, x squared is a perfect square. Right, so we can say, well, we could write this as 5 times, and I'm going to move that up front because this is where I'm going to put it once it's simplified. So square root of x squared times the square root of 3x. That 2 looks terrible. Let me fix that up a little. There we go. All right, so the square root of 4 is 2, so we'd have 6x times 2 times the square root of 3x. And then that should be a minus, not a dot. Minus, there, fixed. Then minus 5 times x times the square root of 3x. All right, and then, all right, so 6x times 2 is 12x, so we got 12x radical 3x minus 5x radical 3x, and both square roots, same radicands, right? 3x under the radical in both. So we can do the subtraction, and 12x minus 5x is 7x. So we've got 7x times the square root of 3x. And that's the answer. So I guess right, and if I just point at this with a different color maybe, right there, I'm working under the assumption that x just takes positive values. But we had that show up in the previous section, right? Where when you're doing these, that's the assumption that you make in order to make life a little bit easier. So if you're looking at that and going, wait a minute, that's supposed to be the absolute value of x. It is the absolute value of x if you allow x to be any real number. So like if x can also be negative. But if you're saying x has got to be non-negative, then it would just be x. So that's why I have it as just x there. So that assumption is kind of carrying through that we had in the last section. So I did want to point that out. All right. Number 5, that looks kind of crazy, and it's actually not that bad. It's different because underneath the radicals, you've got 2-term expressions instead of 1-term expressions. But if you look at those, they have common factors, right? 125x minus 250. 125 and 250 are divisible by 125. Then if you look at the other one, you got a negative 8x plus 16. You go, well, those look like they're both divisible by 8. So there's stuff that we can do here. So let's see. If we just factor out the common factors first underneath those cube roots. So the first one would be factoring out a 125, and we'd be left with 125 times x minus 2. And then if we do the same thing in the second one, remember that if the leading term has a negative coefficient, you should be factoring the negative out. So we should be factoring out a negative 8, not a positive 8. So we'd have negative 8 times x minus 2. And we should be good to go from there, because if you look at what's happening, we've got these products underneath both radicals where one of the factors of each product is a perfect cube. 125 is a perfect cube, so is -8. So we can break these up. And this first one, I'm just going to break it up as the cube root of 125 times the cube root of x minus 2. And then the other one I'm going to break up as the cube root of -8 times the cube root of x minus 2. All right, and then from there, the cube root of 125 is 5. So we have 5 times the cube root of x minus 2 minus, then the cube root of -8 is -2. So minus -2 times the cube root of x minus 2. And we can't break down that cube root any further. So 5 minus a -2, same thing as 5 plus 2. So we'd end up with 7 times the cube root of x minus 2. Fairly simple looking final answer considering what the original problem looked like. So that worked out well. Number 6. All right, if we look at number 6, you go, okay, 11, that's a prime number. We're not going to be able to break down that square root any further. And then the only factors of 6 are 2 and 3. Those aren't perfect squares. So we can't break down those roots. And those roots are obviously different, right? 11 and 6 aren't the same number. So this is one where we can't do anything, right? In order to combine radical expressions, we need like radicals, and we don't have them. So this is one where you can't do anything. And that does happen. I think on the homework it happens once, but this is one where it cannot be simplified. There's no way to get like radicals. It's not, right? That's not the kind of expression that is. So I think that shows up once on the homework, maybe twice, but I think it's once. All right, then 7 and 8. All right, let's see what we got going on here. So with 7, all right, the middle one we can't really do anything with, where there's the cube root of 2x. But with the other ones, I think we can do some stuff with those cube roots. So let's see, -54. The biggest cube root, I guess in terms of absolute value, or I guess the biggest cube would be -27. So I think that's what we're going to want to do with that one, and say that that'll be the cube root of -27 times 2. And then with the x to the 4th, you can also write that as a product where one of the factors is a cube, because you could write it as x cubed times x, right? Because 4 is larger than 3, so you can write x to the 4th as a product where one of the factors is x raised to a multiple of 3. It's just that multiple of 3 is 3 itself, right? Then the middle one, we can't really do anything. So I guess that just is what it is. So 5x times the cube root of 2x. And then on the end, the cube root of 16x, can't do anything with the x, but the 16, that's divisible by 8, right? That's a perfect cube. So plus x times the cube root of 8 times the cube root of 2x. Okay, now let's see what we end up with here. I guess this part I can kind of break up and say, I'll just get the perfect cubes by themselves. So cube root of -27 times the cube root of x cubed, right? That's a perfect cube. And then times the cube root of everything else, which is just 2x. Then the middle, well, we didn't do anything to that, so I guess it is what it was. And then on the end, then that's going to be 2x, right? I guess for now, I'll just write it as x times 2 times the cube root of 2x. All right, cube root of -27 is -3. Cube root of x cubed is x, so we have -3x, sorry, times the cube root of 2x, and then plus 5x times the cube root of 2x, and then plus 2x times the cube root of 2x. All right, well, we've got the root simplified as far as we can get it. And so I guess we can just start combining terms now. So negative 3x plus 5x plus 2x. If you want to jump right to what the final answer is, I think that's okay. It's 4x times the cube root, but I'm going to write it in 2 steps. So negative 3 plus 5 is 2, so we'd have 2x times the cube root of 2x plus another 2x times the cube root of 2x. And, all right, well, then that's 4x times the cube root of 2x. And that's the answer. All right, I think I need to section off number 8 a little bit. 7 is kind of creeping over into the space for 8. All right. At least 8's smaller. I think it's okay if it lost a little bit of area on the page here. Okay, so what we're going to try to do, as before, we're going to see what we can do. Just, can we find perfect squares underneath that radical since it's a square root? That first term, you go, well, a squared's a perfect square, isn't it? It sure is. So you'd have 2 times the square root of a squared times the square root of b. And then watch this. This actually might be hard to see with it in radical notation. So that 6th root of b cubed, I'm going to write that with exponential notation. I think that makes what's happening here a little easier. So you'd have 5a times b cubed raised to the power of 1/6. And remember that law of exponents, where you have a power to another power, you can multiply them together. So, all right, well, I guess we can say that square root of a squared is a, right? We can say this is 2a times the square root of b, and then minus 5a times b to the 3/6. But 3/6 is 1/2 if you reduce that fraction. So I'm going to rewrite that so they've both got radicals in them. So 2a radical b, and then minus 5a radical b. And now we know what to do, right? 2a minus 5a is negative 3a. So it's negative 3a times radical b. And that's the answer. So the weird thing with 8, I think, is that 6th root. So that's the thing that you have to be able to see, that you can actually simplify that. And like I said a couple minutes ago, I don't know that that's the easiest way to see it. It might be easier if it's written with exponential notation. That feels a little bit easier to me, but I guess that's one of those things that's ultimately a personal preference. But either way, like that's the thing you got to see with number 8 to get that to simplify down. All right. The last thing in this section is how to multiply rational expressions. All right. This is like stuff that we've done before. Because if you think about when we would multiply polynomials, like if you had a monomial times a trinomial, you would just distribute the monomial, right? That's the easiest way to do it. And if you had two-term polynomials, like 2 binomials, you would FOIL, right? We've done that a whole bunch. Those are basically the things that you use here. So like it says in those indented bullet points, when you have a 1-term expression by a 2-term expression, so that's like what number 9 and 10 are. So you can see them right now. That's what that is, right? Number 9, the radical 6 is a 1-term expression, and then the 3 minus 2 radical 6 is a 2-term expression. So we're going to distribute. And then if I scroll down a little, if you look at something like number 11, that's one where you'd FOIL. I guess you don't have to FOIL. You could do it as distributing one of the binomials through the other one and then distributing twice, and you would get there. It's just longer. So because foiling is shorter, we're going to FOIL. All right, but that's in the near future. First with number 9. So if we distribute the radical 6, we'd have radical 6 times 3 minus, I guess, 2 radical 6 times radical 6. It looks easier for me to write the radical 6 on the right side there. I should do it in the first one too, just so this looks kind of uniform. So, all right, just flip the order. 3 radical 6. There. Because writing the second one as radical 6 times 2 times radical 6 just felt like it looked too weird. All right, so we're going to get 3 radical 6 there. There's not a whole lot you can do with that. But then, look at what this is down here. Radical 6 times radical 6 is 6, right? Because that's going to be 2 times the square root of 6 squared, right? And taking the square root and squaring, those are opposite operations. You would just end up with 6, right? So this is going to be 3 radical 6 minus 2 times 6. So that's 3 radical 6 minus 12. All right. Let's see if we get a similar kind of thing with number 10, even though this one's got a cube root instead of a square root. So let's see. If we distribute that cube root of 4, I guess we'd have 5 times the cube root of 4 plus the cube root of 2 times the cube root of 4. All right, so 5 times the cube root of 4. Can't really do anything there. But then here, same root, right? These are both cube roots after the plus, so you can multiply what's underneath the radicals. So then that's the cube root of 8. That does simplify, right? That's a 2. All right, so we do kind of get a similar sort of thing going on with number 10. So we'd have 5 times the cube root of 4 plus 2. And that's the answer. All right, then 11, that's a FOIL, we said. And it most certainly is. So let's see. First, you'd have 8 times 5. Then outer, you're going to have 8 times 7 radical 2. Then inner, you'd have minus 3 radical 2 times 5. And then last would be minus 3 radical 2 times 7 radical 2. Okay. What happens with the last part, that product, that's the part that's going to be interesting. So 8 times 5 is 40. That one we knew what was coming. I guess that one's not terribly exciting. And then 8 times 7 radical 2, we could multiply the 8 and the 7 and say that's 56 radical 2. Then 3 radical 2 times 5, you could multiply the 3 and the 5 and say that's minus 15 radical 2. And then watch this part. At the end, 3 times 7 is 21. But then radical 2 times radical 2 is 2. So we're using the same thing that we used in number 9, where we said radical 6 times radical 6 is going to be 6. Right? Here, radical 2 times radical 2 is going to be 2. Right? Different number, but same idea. All right, so then what we could do, I guess in the next step, because I'm going to simplify this to where it's a negative 42 at the end, but we could combine those radical 2 terms in the middle and say, well, 56 minus 15 is 41. So then that should be 40 plus 41 radical 2, and then minus 42. But then you could combine terms a little bit. So I'm just going to rewrite this so the 40 minus 42, and those are right next to each other. So I'm just going to put the term with the radical in it all the way over on the end, basically. But then 40 minus 42 is negative 2. So you'd get negative 2 plus 41 radical 2. All right. So it's foiling, although then there's a new wrinkle that we wouldn't have had if we were just multiplying 2 binomials together, which is what happens with those radical 2's, right? You can multiply a radical 2 by another radical 2 and you get 2. That's a relatively common thing with foiling with rational expressions, although I guess, or radical expressions, not rational expressions. With rational expressions, you wouldn't have this at all necessarily. Although you might. With radical expressions, if you have the same root show up in both, then this is going to happen, right? Because in one of those components of the FOIL, you're going to have to multiply those 2 roots together. So if it's the same root showing up twice, this sort of thing that happened with the radical 2's here, it will happen. So that means it will happen in number 12, because not only are we going to have 2 radical 7's, we're also going to have 2 radical 2's. So with number 12, if you write this out where instead of using the squaring notation, if you just write it as multiplying, so 5 radical 7 plus radical 2 times another 5 radical 7 plus radical 2. All right, if we FOIL that out, we're going to have 5 radical 7 times 5 radical 7, and then plus 5 radical 7 times radical 2 for the outer. But then the inner is going to be the same thing. It's going to be another 5 radical 7 times radical 2. And then the end is going to be a radical 2 times radical 2. All right, so let's see. Right off the bat, the 5 radical 7 times 5 radical 7, we can say, well, this is all multiplying, right? It's really 5 times radical 7 times 5 times radical 7. So you could flip the order around if you wanted to, and it helps a little bit to say, well, we know what 5 times 5 is. That's a 25. And then that's going to be times, well, radical 7 squared, and that's just 7. And then plus, I guess for the outer, we'd have 5 times the square root of 14. And then another 5 times the square root of 14 from the inner. And then the last part, radical 2 times radical 2 is 2. Okay. 25 times 7 is 175. So we've got 175. Then you can add these radical 14 terms together, right? Because they both have radicals where it's the same type of root with the same radicand. So you can add them together and say that's 10 radical 14 and then plus 2 at the end. But you could add the 175 and the 2 and say that's 177 plus 10 radical 14, and that's the answer. All right, then the last one, and notice what happens here. This will be a little bit different in terms of what we get for the final answer. We're still going to FOIL it, but the important thing with 13, and this is really kind of a segue into the next section a little bit, is just watch what you get for the final answer. So we're going to FOIL, we're going to have 8 times 8 plus 8 times radical 5 minus 8 times radical 5 for the inner, and then minus radical 5 times radical 5. Okay, well, 8 times 8 is 64. Then 8 radical 5 minus 8 radical 5, that's a 0, right? Like there's no radical 5 term that we're going to have. But then at the end, we're going to have minus 5. So that's 59. So why is this one so interesting? There's no radical in the answer. That actually ends up being really useful because in the next section, there's going to be a situation where you want to get no radical in the denominator. So like you start off with an expression where there's a radical there, you want to get it out. And the way that you can get rid of it is to multiply by the conjugate. Because that's really what 13 is, right? If you look at what these are, those are conjugates. Right? They've both got an 8 and a radical 5, just one has a plus, one has a minus. And when you have conjugates like that, when you multiply them together, you're going to get an expression that has no radical in it. And it's because those outer and inner terms are going to add out, right? One will be the additive inverse of the other one. And they'll be gone. And then you'll just get an answer that has no radical, basically. As long as, I guess, if you just have the radical in the second term of both expressions like that, then it would work out. But that's usually the way that they're written. So this is a thing that we're actually going to have to use in the future, which is why it's the last one in this section, because it leads right into the next one. So you'll see it in 6.5. What happens in 13 will happen repeatedly.